We are alive, we are alive, we are alive. We are alive. We are alive, we are alive, we are alive, we are alive. We are alive, we are alive, we are alive, we are alive. Okay, let me check. Let me check this. Let me check this. Okay. Okay, guys. We are alive, we are alive, we are. Let's start.
Settle down in the place of dreams. Float away in the scenery. Take a backpack of what you need. Let's explore the world we see. All the dangers have been made up. You believe what they say. Through the heartache, I would stargaze. No invasion today. We've come this far. Through wind and rain alone. So take your chances. Embrace the waterfall.
What is up with y'all boys, man? What is up? Hello, Crosswalker. Welcome to the stream. Which problem? So basically, right now, bro, I'm going to be solving some bit manipulation, some basic bit manipulation problems. And if we have time afterwards, I'm gonna be solving some array problems as well. Okay, welcome to the stream. I'm just gonna leave this and pin. And if we have time afterwards, okay. All right, so everything seems to be okay. Let's turn off this. Everything seems to be working. So let's start. Okay, so I was just learning about some bit manipulation, and I've already like done some solutions here, but we are going to redo them. Okay. Okay, so the first one is check if number is odd or even. So, okay, I'm also gonna comment. I'm also gonna, let's say, delete all of this, all of this. Okay. Since you are starting with bit manipulation, I am starting with bit masking problems. You're gonna solve any of those will be helpful. Uh, uh, Unfortunately, no, because I haven't really studied any sort of bit masking. I haven't really studied any sort of bit masking yet, so I won't be solving any of those. No. Okay, so first one, we're gonna check if a number is even or odd. Now this one is easy. So we're gonna say is even. We're gonna have a number, and then we're just gonna return n, I think, and one, just n and one. Okay. So actually no, it's gonna be is odd, and then we're gonna have our n, which is, and then if is odd of n, we're gonna see out odd, else we're gonna see out even. Let's see if this works. Okay, we get odd. Let's try an even one. Let's see. Okay, we get even. Okay. All right. So, okay, that's that one. Okay, let me pull up the paint here. Let's go into the explanation of this. So, why do we say, how does this give us the answer? Well, we're gonna go into that right now. So what we got here, n is equal to 4. And the binary representation of 4 is 100. Okay, so let's see. Okay, and when we and for with 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 one like this, basically what happens here, we have other bits right here. So basically this is what is gonna happen. So when we AND a number with a number, now both need to be true or one for it to give one. So if it's 0 or and 1 is gonna give 0, it needs to be both 1 and 1 to give 1. Okay, so right here what we are gonna get is this is what we are gonna get. So 0 and 1, that's 0. 0 and 0, that's 0. 0 and 0, 0, 1 and 0, that's 0 again. So, and that is basically what happens. So right now, okay, before I continue explaining, let's try it with n equal to 5 so I don't misexplain something. I mean, keep in mind, I am a beginner in data structures and algorithms. I'm still a beginner in data structures and algorithms, so take my all my explanations and advice with a grain of salt, okay? Take all my explanations and advice of the grain with a grain of salt. I'm just trying to share what I know. Okay? So let's continue with the explanation. All right, int so right now n is equal to 5. The binary representation of 5 is 101. This is 5 in binary. Now, oh yeah, okay, I got it. So basically, when 1, the binary representation of 1 is 001, is 1, just 1. So when we AND 1 with an even all odd numbers, the last bit of every odd number is a set bit. The last bit of a no, not even. The last bit of every odd number is a set bit. So the last bit of any odd number is always 1. And when we do the following, 0, 0, 1. When we do 1, when we do 5 right here, and 1, what are we gonna get? What are we gonna get? Oops. What are we gonna get? We are gonna get, so 1 and 1 is 1. 0 and 0 is 0, and 0 and 1 and 0 is 1 and 0 is 0. And basically what do we get? Well, we get we get 1. We get 1 like this. We get 1. And if I try something like see out 5 and 1, we should get 1. Now don't quote me on this, but we should, yeah, okay, we get 1. So when we AND any number with 1, we get 1. No, if when we AND any odd number with 1, we're gonna get 1. Let's see, 7 and 1. Okay, let's see, 9 and 1. Okay, should get 1 again. Okay, but if we AND an even number with 1, we should get 0, because the last bit of the even number is 0, and that's why we're gonna get 0. All right, so this is the explanation right here. Now, of course, we could also do this the other way, where it's with the modulo, so it can be n equals to 0. But I'm pretty sure that this way, the bitwise way, is faster. I think. I'm not sure. I think it's faster. So yeah. Okay, and that's basically the first problem. Think it's okay. Think the explanation was okay. So get the ith bit. Get the ith bit. So to get the ith bit, there's a couple ways to do this. So I think we're going to have to or, because if 1 or 1 is 1, 1 or is, no, it's gonna be and. So 1 and 1 is 1. 1 and 0 is 0. 1 and 1 is 1. 1 and 1 is 1. So this is going to be with a, okay, first let's try the naive approach to get the ith bit. So we're gonna see get ith bit naive. We're gonna have our number and we're gonna have I. And what are we gonna do? We are going to basically store the binary digits inside of a string, and then we're just going to get the position I of the string, and we're going to get the ith bit. So let's get to doing it. So we're gonna say string binary is equal like this, while n, we're going to say, so how do we get a number converted to a base? We get a number converted to a base by dividing that number by the base, and we're going to get the remainder. Actually, this is not, it should be binary plus equals to string. So the remainder of this is going to be our bit, and then we're going to do n divide equal, and then we divide it by the base. Okay, so now that we have the binary string, we're just going to return binary of I minus 0, and this should basically, this is gonna convert the character into a digit, and this should work. Let's see if this does work. So we're gonna say get ith bit naive, see out like this, see out, then this, and then let's say we want the 0th bit. So the bits are counted from right to left. So the 0th bit is going to be this one. This is the first bit. This is the second bit. So right now we should get 0 if we have done everything correctly. Okay, we get 0. Now if we put 2, now this is the second bit. What should we get? We should get 1 like that. Okay, now this works. This is the naive approach, but it's maybe not that good because we need O of n, or is it O of n? We divide it by 2 on every iteration. So I think it's O of n divided by 2 time complexity, and but I'm not sure. I'm not sure. And maybe I think that strings also take up extra space. Also on that, I'm not sure, but I think they do take up extra space. And so this is an O of, if that is the case, then this is an O of n space complexity, if that is the case. If that is the case. So, okay. Yeah, that's basically the naive approach. Now, what is the optimal approach? What is the optimal approach? Get ith bit of int n and int I. What do we have to do? To get the ith bit, we need to do the following. First, we are going to move n to the right, shift to the right by I. So what is this gonna do? Right shift, this is called right shift. What does it do? It shifts the number right to the right by it shifts the binary representation of the number to the right depending on what we put here. So if this is 1, it's gonna shift it to the left by 1. So if I is equal to 1, then it's gonna be 1 0 0 left shift 1, which is gonna be 1 0 0 1 0. Okay, so this is why we shift by I, and then we're gonna say and 1. Now if the current bit we have shifted to the right this many times, and now we are on bit number I. So let's say we shifted once. So now this is the binary number we have. This is 2. It's 1 0. So 0 and 1 is going to be 0. So we're going to get 0. We're going to get 0. But if we have something like 5, something like n equal to 5, and then okay, maybe not 5, maybe 6. So 6 in binary is 1 0 is 1 1 0. So when we left shift 6 by 1 is going to be equal to 1 1. Okay, and now we are going to get, and this is now the number, this is 1, this is 2, so this is 3 right now, but that's not important. What's important is that now we're going to get this bit right here. We're going to compare this to this, and now is 1 and 1 1? Yes, it is. So this is gonna return 1. Okay, now let's say I is equal to 6, I mean n, and then we're gonna do get ith bit, but the not naive approach, and this should give us 1. Should give us 1. Okay, if it's 0, it should give 0. Should give 0. And then if it's 2, so 1 2, this should give 1 as well. Should give 1 as well. Now if it's n is 5, let's just see out n, and this should give me If we said 0, this should give me 1 because it's an odd number, so the first bit is gonna be set, so it's gonna give me 1. There we go. Okay, that works. That works. Okay. All right. So next one. There, as we can see, that's that right there. Set ith bit. So set ith bit. What does that mean? That means that whichever bit I we go to, if it's 0, we need to make it 1, and if it's 1, it's gonna remain the same. So first, let's do the set ith bit naive. We'll have int n, and we're going to have int I. So what is a naive approach? Well, again, we're gonna use a string binary to get the binary representation. Going to do the same as before, which is the same as before, plus equals to string binary, non-binary, n by 2, then n divided equal 2, and then we're going to uh, binary of I is going to be 1 is a string, and now we're going to say for char c in binary, and we're going to so now we get now we got the binary representation. We have our new numbers. All right, so now we're going to do power, because we're going to convert this from binary to decimal again. We're going to say n plus equals power of 2 to power times c minus 0. This gives us the bit. This gives us the bit, and this is gonna, so if it's a character 1, this is gonna make it an integer 1. Then don't forget to increment the power, because that's gonna, yeah. Okay, I think that's it. And what is this? Is set ith bit naive. Okay, so we're going to say set ith bit naive n, and we are going to set the first bit. So this should become 7. Going to see out n, and we should see 7. We should see error definition of voice set. Okay, my bad. So I didn't. What did I do? I did not. I forgot to comment out all of these. Need to comment out all of these. I was already practicing a little bit before the stream, so I can be better at explaining. Chat should be char. Okay, and we get 7. There we go. So this works, but this again, this is n divided by 2, or n divided by 2. This is slower. I'm pretty sure it's, I mean, basically the bitwise operations are all of them basically are O of 1 time. So this shift right here, it takes O of 1 time, and this and also O of 1. So right now we're going to do the void set ith bit of int n it's gonna be int I, and then this is just what we're gonna do. So right here in the previous one, we were getting the ith bit. Now instead of getting the ith bit, we are going to, instead of and right here, we just need to put or. We just need to put or. So n is equal to n to the I, or wait, no. So n is equal to n or 1 to the I, 1 left shift by. Okay, so yeah, it's not the same, my bad, it's not the same. So what is it gonna do? So let's see, we have 1 initially. When we left shift 1, actually this, yeah, left shift let's say by I is equal to 1 or something. And then when we left, one left shift 1 is going to be equal to 1 0 1 0. And then if uh, let's say that n is equal to 5 equal to 1 0 1, and then 1 0 1 or 1 0 is going to be, and this basically right here, and then basically this is going to be 1 1 1 like this. Okay, so let's get another number here. Let's say equal to 4 and 2. We're going to see out and 2 and 2. Then we're going to say set if bit and 2. That's going to say into before, and then it's gonna be into, we're going to set, let's say that's 0 bit, so this is gonna create, then it's gonna make it 5. So we're gonna have set into after and 2, and this should first should be 4, then it should be 5. Yeah, 4 and 5. Okay. Okay. Okay, next one. Next one. Yeah, like this. Clear if bit. So basically what this means, we need to make the bits at position I, we need to make it 0. So again, first let's do a naive. First let's do clear if bit naive. Wait, didn't I just clear if bit? Wait. Clear, oh, what was it? Okay, pretty sure I did. Int and n, int I. We're gonna have our string binary. We're gonna have while n. We're gonna have while n. We're gonna have binary plus equals to string of n like this, and then n divide equal to. Then we're gonna say binary of I is equal to 0, and then we're going to convert this back to decimal. Our power is gonna be 0, so for char c in binary n plus equals pow 2 of power times c minus this, and then power is gonna be plus plus, and then this should be it. Okay, so let's say we're gonna clear if bits, but not oh yeah, naive of n2, and then it's gonna be let's say 0, so this should give me cout n2. This should give me 4. Should give me 4. Okay, we get 4. Let's try another one. Let's try, say we want to clear the second one. Now this should give me 1. There we go. And that's basically the naive one. Let's do the optimal one now. So to clear the if bit, to clear the if bit, basically what we need is a bit mask where everything else except this one is, so every other in our bit mask, everything else besides the position I should be a 1. So this should be a 1, this should be, so this is 1 0 1 1. That's what our bit mask we want to be. So we're gonna say clear if bit of int n and then int I, and then we're going to say n equals n and not 1 left shift by I, and this should work. Now if we say clear if bit of n2 and say 0 and cout n2, this should give me 0 now since it was 1. Yes, we get 0, and let's just say n2 is equal to 7 right here actually, and then we're gonna see out, then we're gonna clear the if bit, and that should give me 6. Should get 7 and 6. There we go. Okay. Okay, so basically I'm gonna try to pull up the paint for this one as well. So this was the, okay, I have to make it big again, kind of annoying. So basically, why does this oops, what? Why does this bit mask work? So let's take the example of, let's say that n is equal to 7, and let's say that, and then the binary representation is 111. This is 7. So this is 7 in binary is 111. And then when we do one left shift by, let's say, 1, this is going to give us 1 0 like this. Okay, and then when we say okay, not this, when we say where is the, okay, this one, when we say not of this, it's going to flip, it's going to, okay, what is like this, maybe it's going to flip, so all of the ones are going to become zeros and all the zeros are going to become ones. So basically 1 becomes 0 and 0 becomes 1, and then and everything else is 1. So everything else to the left is 1 as well. So when we have, this is what happens now. This is what happens now, and we have and here the answer is gonna be, we're going to clear the if bit. We're going to clear the if bit. In this case, I is equal to 1. I is equal to 1. Okay, right here. And what we are gonna get is 1 and 1 is 1, 0 and 1 is 0, and 1 and 1 is 1. So now we get, now and after all that, n is equal to 5 after clearing, because this is like this is 1, this is 2, this is 4. Okay, and so 1 plus 2 3 plus 4 7, 1 plus 0 1 plus 4 5. Then that's basically that one. That's basically that one. Which is the best laptop for hardcore coding and medium gaming under 1 lakh? Hey man, hello Aditi, welcome to the, first of all, welcome to the stream. And after and then what I to be honest, I cannot tell you. I don't know that much about hardware. I'm not really familiar with what computers are best, but this one that I'm using right now is has a six. I couldn't tell you what is the best laptop at a certain price, but I can tell you what I'm using. What I'm using, this laptop has 16 gigabytes of RAM, but I'm pretty sure that even with 8 gigabytes of RAM, you would be able to program without any problems. I actually have programmed on a laptop with only 4 gigabytes of RAM and it ran pretty well, but I'd say to be in like that safe spot, you need a laptop with at least 8 gigabytes of RAM. I'd say. And I must say again, I'm not an expert in hardware and things like that, so I'd suggest if you, I would suggest that you Google or like uh, ask Google or something like that. Yeah. Okay, we did clear I've bit. Yeah, we did this. Now toggle I've bit. So what does toggle I've bit means? What does this mean? It means if the I've bit is 0, we're gonna make it 1. If the I've bit is 1, we're gonna make it 0. Okay, that's basically what that is. All right. So first, and I'm telling y'all, I'm still a beginner. I don't know if I think we use XOR with this because one XOR with I think we use XOR because one XOR with one is 0 and 0 XOR with one is 1. Yeah, we use XOR for this, but the XOR is the optimal solution. First, let's do the naive one, which is toggle if bit naive, and we're gonna have our number, we're gonna have our index, we're gonna have string binary is equal to this, we're gonna have while n, we're gonna have binary plus equals to string of n remainder, and then we're gonna have divide like this, and then binary, and then we're gonna say if binary of I is equal to 1, binary, then we're gonna say binary of I is equal to 0, else binary of I is gonna be equal to 1. So this is how we're gonna toggle it, and then lastly we're going to just make this into a number, a decimal number again. So we're gonna have 4 char C in, or if what, let's say bit or something in binary. We're gonna say n plus equals power of 2 to the power, and then times bit minus this, and then we're gonna go power plus plus. And again, man, I don't know if this is the best way to do this in the naive way, but it seems to work, so that's why I'm doing it. Okay, we did that. Toggle I've bit, and then we're gonna say cout before toggle let's say 2 bit. We're gonna have n2, and then we're gonna say toggle I've bit naive of n2 and 2, and then we're gonna say cout after toggle 2 bit and 2. Okay, after toggle. Okay, So let's see. So right now it's what? It's 6. So when we toggle, let's actually toggle the first one. So we make it 4. So we make it 4. Okay, should get 4. Okay, we get 4. Now let's toggle a bit naive. Let's toggle 1 and then toggle a bit naive. Okay, first let's toggle 1. No, it's actually 0, so we get 5. And then we're gonna say after toggle 0 bit, this should give us 5 because it should turn that bit from 0 to 1. There we go. And then let's say we're going to toggle if bit naive event 2 with this one is going to be 1, and then we're going to say after toggle 1, yes, this should give us 7. Okay, we get 7. Okay, and that's the naive approach. That is the naive approach. So let's now try the okay, actually let me let me just where is the okay, let's just do this to 20 so you guys can maybe see this better. Okay, okay, all right, okay, we did that. Now let's do the naive the not the naive, the optimal. So toggle if bit. So what you need to use here is XOR. So we're going to say n equals n and actually not n XOR 1 left shift to I, and then we're going to say toggle if bit and 2. We're gonna toggle the first the 0th, and then we're gonna say after toggle 0 bit we should get 6 again, not 10. We should get 6 again. Let's see if we do. Okay, let's now toggle the bit of n2. Let's toggle the second bit, and now we should get 2. Now we should get 2. We should get 2. Okay, we get 2, and then let's toggle the 0th bit, and now we should get 3. We should get 3. Okay, there we go. That's about it for that one. Okay, okay, okay. Okay, we toggled the if bit. All right, so let's go next one. Count number of set bits. Okay, this one I think we're just gonna have to do it with the more naive approach because uh yeah, we're gonna shift right check last bit. We're gonna loop through bits. Okay, okay, we really have a lot in here, so maybe let's comment just to get rid of some of this. We're gonna okay, so now we have count number of int count number of set bits of n so we're gonna say counter equals to 0 while n we're gonna say if n and 1, meaning if the current bit is what is a set bit, we're gonna say counter plus plus, and then we're gonna say and like this, and then we're gonna return the counter like that. Okay, return the counter. Okay, and now let's try this. So cout count number of fit bits of n, and this should be 2. Now let's say 7, this should be 3. All right. Okay, so what happens here? So this is basically checking if the last bit in the current binary representation is 1. Then if yes, we're gonna count. And when we right shift, we shift the last bit to the left because the shortest bit to the left becomes the last bit to the right now. So if we have 1 and 1, this is gonna be equal to 1. So counter so counter plus equals 1. Else we're gonna do nothing. And n, and basically n divide not divide like this is same as n equal n like this, and then if n equal to 7, then n left shifted by 1 equal to 1 1 1 left shifted by 1 is equal to 1 1. And that's basically it. And at some point we're gonna left shift right shift so much that this is gonna become 0, and then the loop will finish, and that's when the function is gonna be over. So this is gonna be 1, and with 0 is gonna be 0. Okay, all right. Okay, that's basically that one. Yeah. Okay. Now it's gonna check if power of 2. Hmm. Yeah, this one. Okay, I haven't gotten to this one. Um, we can try to bool is power of 2 int n return, and we can dry run this to make it clearer. We can dry run this to make it clearer. Okay, so we are going to, okay, no, it's n minus 1, right? Yeah, n minus 1. So basically, if we have a number such as 16, which is in binary, it is 1, 1, 2, 3, 4, and actually it's 15, which is 16 minus 1. In binary, it is 1, 1, 2, 1. Or is it? Where is it? Uh, this is 1, 2, 4. No, it's like this. It's like this. Wait. 1, 2, 3, 4, 5. Okay, I'm gonna check 15, 15 in binary. Okay, it's 1, 1. Oh, yeah, my bad, my bad. My bad, guys. It's 1, 1, 1, 1, which is 4. Yeah, so this is 1, 3, wait a sec. 7, 15. Yeah, because this is 1, this is 2, this is 4, and this is 8. So 1 plus 2 is 3, plus 4 is 7, plus 8. That is 1, 2, 3, 4, 5. That is 15. And basically when we have 1, 0, 0, 0, 0, and we have it and with 0, 1, 1, 1, 1, what happens is it's going to give the following. So it's going to give so oops, it's going to give so 1. Okay, so 1 and 0 is with 0. Then this one and everything else is gonna be 0. Everything else is gonna be 0. So is this a power of 2? Wait a sec. It's 16 and 0. No, wait. 2 and n. Then I'll just check powers of 2. Okay, yeah. Okay, I'm don't getting I'm missing something. I'm missing something. Um what am I missing? What am I missing? Hmm. 1, 1, 1, and minus 1. So let's see. But is power of 2 with 4 gives 0. But 4 is a power of 2. And n minus 1. What am I doing wrong? I have no idea what I'm doing wrong. The opposite of what you want. Okay, so we're not gonna do this one right now. We're going to do the next one, convert decimal to binary. So we can do this with this and division or bit shifts. We're going to do this with bit shifts. Okay. So we're gonna say it's decimal to binary and n, and we're going to do this. Let's say int binary equal to 0, while n, we're going to say binary plus equals wait a sec. If we say, let's try it, n and 1, and then let's say, I think it's n, let's shoot by 1, I think. Okay, let's return this, and then let's see what this gives us. No, it should be binary. Do see out binary, no, decimal to binary of 5. Let's see what we get. Okay, we need to binary times equal 10, I think, or something like that. Okay. Okay, so binary divide equal 10, and this should remove the last one. Okay, so that's 1 on 1. Let's try to get 15. Okay, we get 15. Okay. All right. Okay, and that works. Okay, convert binary to decimal. I mean, we've kind of already done that, but binary to decimal, int n, this decimal is going to be equal to 0, int power is going to be equal to 0, while n decimal plus equals to power of 2 power times ampersand 10 power plus plus, and divide equal 10, and then return decimal like so, and then let's see, binary to decimal 1111. This should give us not 19, this should give us 15. Okay, we get 15. Let's try this. This should give us 7. It should give us 7, and then let's try this. This should give us 5. Okay. All right. Okay. All right, guys. So we're almost done. Let's try to do another one. Find single number. Okay, this one is simple. Let's see. Find single go number vector int r. Okay, so we're gonna say int ans is equal to 0 for auto int for auto, and in r we just need to do this ans xor equals n. So why does this work? Because when we have values which duplicate, which appear an even number of times, 2 XOR 2 is 0. Any number XOR with itself is equal to 0. And any number XOR with 1, not with 1, with 0 is equal to that same number. Okay? So, and then we're going to return ans. Alright. So, then we're gonna have this. Gonna have this. Okay. Have a vector int array is equal to this, like that. And now find single number is going to be, I'm just gonna pass the array, and what we should get is 1. 1. Okay, but if we say 1 like this, we're gonna get 0, because you know. But if we say 3, we're gonna get 3. So this is actually a problem on lead code, and you guys can try to go to lead code and solve it. And yeah, okay, let's do this one, and then we're gonna call it a day. So we're gonna say manual, so void manual, or actually let's say bitwise swap. We're gonna say int a and int b. So how do we swap this without doing, so the usual way to swap is like this. So we set temp to something, we set a equal to b, and we say b equal to temp. But in an interview you might get asked to do it without this way. So what do? We do a equals 1 XOR b, b equals a XOR b, a equals a XOR b. Okay, let me see if that's actually it, because alright, so it's to disallow. Okay, yes, like this, and this is the explanation. So first, a is equal to a XOR b, then b is equal to a XOR b. Now what is a? A is a XOR b. So it becomes a XOR b XOR b. A number XORed with itself always gives 0, so we're gonna XOR b with b, and then this is going to give us 0, and then we're going to be left with a. So now b is equal to a, and finally a is equal to a XOR b. Now what is a? A is a XOR b, and so it becomes a XOR b XOR b. Now what is b? B is a. So finally we get a XOR b XOR XOR a XOR b XOR a, which gives us b. And now b is equal to a and a is equal to b. Okay. So where is this bitwise swap? Okay, so we're gonna have int a equal to 4 and the b equal to 5. We're gonna say cout before swap. We're gonna say a b, and then we're gonna say after swap. We're gonna say A, B. Okay, and as we can see, these will be swapped. It will be swapped. Oh wait, I did not call the function. Swap bitwise swap A B. Okay, actually we need to put it here. Okay, no, and now this should, there we go. It was 4 and 5, and now it's 5 and 4. Okay, guys. Okay, guys, that's gonna be it for today's stream. Make sure that you like, comment, and subscribe. And we're gonna be streaming tomorrow at the same time, 5 p.m. EST. Thanks to everyone who joined, even for a little bit. And I will see you guys again tomorrow. I will see you guys again tomorrow. And I'm gonna say thank you so much and bye bye. Take care.